Hi everyone, welcome back. This is the last lecture of this series on the alpha chromatic symmetric function. We already had Misu and Jim to teach us about the background and also some proofs on the paper. And today will be the third author, Jason, will be giving us another lecture on talking about the alpha chromatic symmetric function. All right, Jason, go ahead.
Yeah, thank you for the introduction. And thanks for the organizers to give me an opportunity to speak here. And thanks for Misu and Jim to share the opportunity. Um, as Misu gave a wonderful introduction and give a motivation to study alpha chromatic symmetric function, and Jim introduced two major techniques in our paper. So today I'm gonna talk about results of our paper, but I have to recall some stuff and I have to motivate you. So maybe some of it will be overlapped with Misu and Jim's talk. Okay, let me start. So let's recall the definition. So pi is a thick path of size n. Then we define the alpha chromatic symmetric function denoted by x alpha I. Um, this is defined by Carson-Mellitz relation. So let's recall Carson-Mellitz relation first. So it says the usual chromatic symmetric function is given as a statistic substitution of unicellular LLT divided by 2 minus 1 to the n. And here it's a usual chromatic symmetric function. And think of this statistic substitution as a q to the 1 minus 1. And if you replace this 1 here as alpha, then you get this alpha chromatic symmetric function. Okay, and this guy uh, is a symmetric function in two parameters, q and alpha. And you can see that the coefficients in alpha is a if you specialize q equals to 1, you can see the coefficients are polynomials in alpha. So with q, we will consider two bases, maybe two bases for the polynomials in alpha, but in q version. The first one is alpha binomial coefficient, alpha plus k choose n, so q integer, q binomial coefficient, where k ranges over 0 to n minus 1, and alpha falling factorial basis, where k goes 1 to the n. We will call it alpha binomial basis and alpha falling factorial basis. We'll see various positivity results involving these two bases. And before I'll go to introduce some results. I'm gonna give you some motivation, which Misu already told, but also I'll go very quickly. So, main motivation for me personally was this mental picture of Ward-McDonald polynomial. So if you study Macdonald polynomial, everybody says Macdonald polynomial, but mainly two different Macdonald polynomials are called the same name. So there is Macdonald J or P, or maybe Jack polynomials, and the modified Macdonald polynomials. And I'll just call it integral form Macdonald polynomial. And from right-hand side to left-hand side, to obtain left-hand side from right-hand side, you have to take platistic substitution. And this platistic substitution is very similar to the way we obtained the chromatic symmetric function from the unicellular LLT polynomial. And more interestingly, lots of things are in common in each word. So in the right word, the combinatorics of it is governed by fillings or general words, and the combinatorics in the left-hand side is governed by non-attacking fillings or maybe proper colorings. So non-attacking filling is something like if your two spots are attacking each other, then the filling of these two spots should be different. So it's kind of a proper coloring like thing. And more interestingly, there's the right-hand side. These two guys are sure positive, known to be sure positive. And in the left-hand side, there are some E positivity conjectures. So this conjecture is from, so I'll just write conjecture. So it's maybe inspired by Hagelin and Wilson and um, myself. We could conjecture that the E positivity of Macdonald J polynomial at t equals to q minus k. We have to divide some q minus 1 factors, but I'll just keep it this way. So there are some similarities, like in each word, like some these guys are E positive in some sense, and this guy is famously E positive by Stanley-Stanbridge conjecture. And the other conjecture concerning the left-hand side was Alexanderson, Hagelin, and Wang's conjecture. And they conjectured some modification of Jack polynomial, which I'm not going to talk about the modification, but this guy is sure positive in terms of alpha plus k choose n basis or alpha falling factorial basis. So, so these are two main motivations. So we wanted to study the E positivity of chromatic symmetric function, which is Stanley-Stanbridge conjecture. So everyone wants to prove it, but no one was trying to prove this conjecture in terms of chromatic symmetric function because there was no alpha version. So that's why we have defined the alpha chromatic symmetric function, mimicking the way we obtain this Jack polynomial, and try to see this phenomena also holds for alpha chromatic symmetric function. So these are computation of alpha chromatic symmetric function. I should put it so for simplicity, I specialize q equals to 1. And here, pi, I denoted by 233, which is the height of each column. So the dict should be like this. So it's 2, 3, 3, okay? And if you compute the alpha chromatic symmetric function and expand it into monomial basis, you can see that this is not positive in alpha to the k basis. So it's not positive in the polynomial in the usual sense. But if you expand it into alpha folding factorial basis, it is not only positive in monomial symmetric function, it is also Schur positive. So you can see that alpha chromatic symmetric function at q equals to 1 is positive in alpha following factorial basis, and you can also see the positivity, the Schur positivity in terms of alpha plus k choose n basis. So these are an example of a conjecture or observation, which is analog to the Alexanderson, Hegland, and Wang. So if you further observe, if you put Q in it, and if you compute some alpha chromatic symmetric functions and expand it into Schur bases and expand each coefficients in alpha into these two bases, you can observe that this alpha chromatic symmetric function can be positively expanded into these two bases. So alpha plus k choose n times Schur or alpha following factorial times Schur. Okay. So this was my motivation to study this alpha chromatic symmetric function, and but this is not the only reason we study these conjectures. So why do we care? So to say that, I'm gonna introduce a proposition. So let x the alpha chromatic symmetric function, and let's expand it into two bases. And say maybe okay, doing it. And in terms of second basis, D, okay. Then the unicellular LOT polynomial has a Schur expansion like this. So its Schur coefficient is given by the sum of the first coefficient divided by n factorial, or it can also given as the last d coefficient. So this is n. This is sum the last d coefficient should give the Schur coefficients of LLT polynomial. And you can easily prove this using Carson-Mellett relations. Then taking alpha to infinity. Yeah, I may have to normalize in some sense, but I'll just keep it this way. So one remark is that, okay. So this was another motivation to study this Schur expansion of alpha chromatic symmetric function. Because if you can find the combinatorial interpretation of this C, then you can almost have a combinatorial it's not a combinatorial interpretation, but you can have some nice formula for the Schur expansion of unicellular LT. And the second one is more direct. So if you can expand this alpha chromatic symmetric function into second basis, then the last ones are just the Schur coefficients of LLT. So one remark is that the chromatic symmetric function, the usual one, is given by the last C coefficient and also the first D coefficient. Oh, sorry. And the first D coefficient. Okay. So, and somehow, so Jim last time he mentioned about this one here, this one here. So finding the Pauling factorial basis is more difficult to finding the Shor coefficients of unicellular LLTs. So I thought finding this one might be a little more easier. So uh, so for me personally, I was trying to find this alpha plus k choose n basis, the coefficient in terms of those bases. Okay. And here's the results. So this is results of our paper. So we studied positivity and combinatorial expansion, combinatorial formula of alpha plus k choose n basis in terms of Shor, alpha plus k choose n in terms of monomial, and alpha falling factorial in terms of Shor. And we know the positivity here, but we don't know the combinatorial formula for this alpha plus k choose n basis. So the next thing we can ask is, even though we don't know the Shor coefficient, can we find the monomial coefficient? And so positivity just follows. And the answer is yes here, and this is today's main goal. Okay. And for the second basis, we don't know nothing about because it uh as I said, this in terms of this alpha folding factorial basis, the D coefficients, the first one is just the Shor coefficient of usual chromatic symmetric function. So we know positivity, we know combinatorial expansion. And the last one is Shor coefficient of LLT polynomial. So we know the positivity, but we don't know the combinatorial expansion. But the coefficients in the middle, like d, pi, lambda, k in general, we don't know the positivity yet. So I think it should have some nice geometric interpretation first to prove this Shor positivity. It's out of my hands, so I'm not going to talk about this. One other thing is that even though we don't know anything about alpha falling factorial basis, but at q equals to 1, so it's general q word, but q equals to 1 word, we actually know that the in alpha falling factorial basis, our alpha chromatic symmetric function is E positive. And I'm not gonna talk about it a lot, but I'll just mention that using XY techniques that Jim told us 2 days before, we get the following theorem, expanding this alpha chromatic symmetric function at q equals to 1 as a okay, in following factorial basis and each coefficient of this following factorial basis is a symmetric function. And this symmetric function is nothing but a sum of certain chromatic symmetric functions. So this one here, this guy here is a usual chromatic symmetric function. And this beta here is certain dict path associated to S. And this S comes from, this is a set of set partitions of N into K parts. So there is certain way to decompose this alpha chromatic symmetric function as a sum of just usual chromatic symmetric function. So if you know some positivity results of chromatic symmetric function, you automatically get the same positivity results for alpha chromatic symmetric function at Q equals to 1. So using this theorem, and if you add Nikita's proof, Nikita's results, then you get alpha following factorial E positivity. And if you want to add Gaussian results, then you could also get the alpha following factorial times Schur expansion. So it's kind of an automatic from this theorem. Okay. But today I'm going to focus on the monomial expansion into this binomial alpha plus k choose n basis. Okay, let me fix partition lambda and the dict path pi, of size n. And then let W lambda be the set of words of type lambda. By the words of type lambda, I mean the number of ones are lambda 1, number of twos are lambda 2, and so. Okay. And for a byword, W comma sigma from this W lambda times the permutation group as n, we say an index I is called an ascent with respect to pi. Oh, sorry. Ascent of I is called an ascent of this byword W comma sigma with respect to the dict path pi if, so we call, for a word, we call an index is an ascent if Wi is less than Wi plus 1. So it's a byword, so we have to compare Wi comma sigma I with Wi plus 1 comma sigma I plus 1. And I'll talk about how we compare this. So if Wi is less than Wi plus 1, then it's an ascent. Or Wi is same as Wi plus 1, then we compare sigma I and sigma I plus 1. But in this time, we compare these two with respect to pi. And to recall this, recall, let's say this is a dict path, and we say I is less than j in pi if this cell I comma j is above the dict path. So if Wi and Wi plus 1 are the same and sigma I is less than sigma I plus 1, in this sense, we call I is a descent. Ascent. and define ascent as the number of ascents. Why, okay. And we need one more thing. Oh, I haven't written. Okay. We need one more thing. It's an additional stat of this sigma, W sigma, which is very complicated. So I'll just write it and I'm not going to explain it at all. So it's in pi of this guy plus, you can find it in our paper. Okay. So it's in pi restricted to this inverse image, and this permutation restricted to this inverse image, plus n choose 2 minus n n k plus co-match, whatever it is, of this W sigma. And I just defined this additional statistic, which is not important in this talk, to state this theorem. Okay. So this alpha chromatic symmetric function we can expand it into monomial basis, and it's q to the stat pi of W sigma times alpha plus cent of W sigma. Choose n, where the sum is over W lambda times Sn. Okay. So we collect all the bywords here, and somehow this stat, it gives you the right additional statistic, and this ascent statistic gives you the right k in alpha plus k choose n basis. Okay, and let me give you an example. So as in our running examples, our pi is this guy. So it looks like this the path. So we only have one relation, one poset relation. One is less than 3 with respect to pi. Okay. Then let me give you two examples of bywords. Let us choose lambda to be 2, 1. Then W lambda is a set of words with 2, 1 and 1, 2. I mean, it sounds a little little weird, but so I'll just, yeah. So there are two ones and 1, 2. Okay, so it's these three words are in W lambda. And you can take maybe 1, 1, 2 with a permutation 1, 3, 2, or you can take 1, 2, 1 with the permutation 1, 3, 2. Then since these guys are the same, you have to compare these two. And since one is less than 3 with respect to pi, so this first position is an ascent. And in the second position, since one is less than 2, it's also an ascent. And in the second byword, since one is less than 2, it's an ascent. But since 2 is larger than 1, so it's not an ascent. So in the first case, ascent is 2, and in the second case, the ascent is 1. Okay, and this is the table of all bywords of when lambda is 2, 1. So when lambda is 2, 1, you have 3 words, and for each 3 words, you have 6 permutations. So you have total 18 bywords. And if you compute the ascent statistic, you can see that there are only one bywords of 2 ascents, and there are 5 bywords of 0 cents, and rest of 12 bywords are they have 1 cent. So this comes from our computation, and if you can see that this number 5, 12, and 1 comes from our theorem. So our theorem just matches in this example. Okay. Uh, okay. So how we prove this? Uh, to prove it, we have to use superization techniques and then some bijective argument. So let us recall some superizations first. Oh, and first of all, we prove the claim for alpha in positive integers. So since it is like polynomials in alpha, so if you can prove this in uh like infinitely many alpha, then you can prove it in general alpha. Okay. And as Jim told us yesterday, if you use superization of this guy, then so if you think of this LOT, it's just putting ones in all diagonals, so there is only one. But if you think of this q to the alpha minus 1, you can choose 1 or minus 1 because you're considering superboard with only one alphabet. And if you remember, you can collect the possible ways for each position. And if you divide q minus 1 to the n, then it goes something like a root product. So that's what Jim has explained yesterday. So using the superization technique, we could prove this root product like formula as alpha minus the area sequence of this dicta. Okay. And by the Carson-Mellit relation, this is just a chromatic symmetric function of this guy. And this is by definition. So this, you can just put variables like alpha variables and replace it as 1q and q to the alpha minus 1 in the chromatic symmetric function. Then what you get is the sum is over proper alpha colorings. So let's just say we take any words in alpha alphabets 1 through alpha minus 1, which is proper colorings of pi. Then you have to count the inversion, and you also have to count, because you have these guys are replacing the variables, you have to uh, take the sum of the sigma, like sum of the numbers in the sigma. Okay. And we will use this identity, refer this identity as star. Okay. And let's start over. So this was superization when x is just 1, but let's use the superization again with x. Okay. So this guy is sum over all colorings non-proper 2 due to the in times monomial. And you can take superization where x goes to q to the alpha x and y goes to epsilon x. Then what you can get is a formula for 2 to the alpha minus 1. And I'm not gonna explain what this is, and dividing both sides by q minus 1 to the n, we get the alpha chromatic symmetric function in the left-hand side. And we get some complicated stuff in the right-hand side. So it should be a little more complicated than the first one because we are considering x here, but it's quite similar. So it counts the in, and then the product looks like the product of this form, but with a smaller dict path. Okay, so area of the dict path, but restricted to the inverse image of C, inverse image of I with respect to C. So C is just a word, and let's say C is 1, 1, 2, then C inverse of 1 is 1, 2, and C inverse of 2 is 3. Okay. And you can obtain smaller dict path by restricting your up steps and right step in the these two or this one. Okay. So for example, let's say pi is 2 to 3. It looks like this. And if you restrict pi to 1, 2, then what you do is actually, so you collect these up steps and right steps for 1 and 2, up steps and right steps, and collect it all together to get this. Okay. So this is like two small example, but hope you can get the idea. Okay. And then the root product. Lambda I alpha minus aj of pi c minus I. So you're actually doing the same thing, but for each I. Okay. So you can replace, since this one here is the same as this one here. Okay. You can replace this guy using star, and this guy will become alpha decorated colorings because, okay, so first you think of coloring C, but it's just a word. You don't have to be proper, but in each inverse image of C, so if your C has color in the same, then in that case, your alpha colorings will distinguish, it will make it proper. So somehow this star identity will give you this formula as CD of n lambda times, okay, I'll just write it C proper coloring, alpha decorated proper coloring, and similar statistics. The product of to the in. You don't have to follow all these, but what I want to say is that, okay, all these are q to the some power. So you can replace this product, sum of product, as a sum of like q to the something. And this sum is over this alpha decorated proper coloring. So this as a set is C comma D in W lambda times alpha coloring, where which is proper. Okay. And now our test. is to collect this guy. C alpha pi lambda correctly to get the alpha plus k choose n. Okay. So there are a bunch of q to the some power, so you want to collect some of it to make it alpha plus k choose n basis. Okay. To do so, we introduce bijection C, which goes from the the byword W lambda times Sn, where the ascent is K, times alpha plus K choose N with C alpha pi lambda. So somehow we are collecting the alpha decorated colorings in alpha plus K choose N many things to get this bijection. And here, this alpha plus K choose N is the set of N numbers where each Ti is between 0 and alpha plus K minus N, and this is weakly inclusive. And you can think of it as a path in this N by alpha plus K minus N. And if you think of any path from 0, 0 all the way to here, then recall the height as tau, then you will obtain length n sequence, and number of it will be alpha plus k choose n, and it satisfies all these conditions. Okay. And what we have to do is define W phi of W sigma and then tau. Okay. And we'll define it as a alpha decorated proper currents. So we'll define it in sigma I. So sigma I position, in sigma I position, the first coloring would be WI, and the second coloring should be given like this, minus ascent of W sigma up to I. So this guy is a number of ascents occurring in the first I minus 1 positions. Okay. Yeah. And I'm not gonna go into details, but I'll just give you some examples. So in our running example, lambda is to 1. And as I said, we have to choose alpha to be positive integer. So let's say alpha is 2. Okay. Then in the left-hand side, what we have is, so when alpha is 2, then alpha plus 1, no, alpha plus 0 choose 3 is 2 choose 3, which is 0. So it vanishes. And alpha plus 1 choose 3 is 3 choose 3, 1. Alpha plus 2 choose 3 is 4 choose 2, 3 is 4. Okay. So we'll multiply all these blue ones as 0, and we multiply all the other 12 guys with 1, and we multiply this guy with 4. Okay. And if you count the So we have four of these guys, like the tau should be 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1. So there are four of them. And all the tau here should be 0, 0, 0. Okay. So there are total 16 of them. And this phi bijectively correspond to proper alpha decorated proper currents. And if your first coloring is 112, you could also have 121. You could also have 211. And your second coloring comes from 1001 to the 3. But using this D, you have to have a proper coloring. Since these two guys are the same here in the first coloring, you should distinguish these two colorings using D. So these not all the eight of them. In D you should have these four. So these two are not the same. Okay. And for this guy, since C is already proper coloring, so D can be anything from this 0, 1 to Q. Okay, so there are eight of them. And here, since we have uh, this equation, so we have four choices of D. So in total, we have 4, 8, 4, which is 16. So somehow this phi bijectively correspond the this in the left-hand side with the alpha decorated proper colors. And then using this bijection, recall that we have obtained a monomial coefficient as a sum of these alpha decorated proper colors. So somehow using this bijection, we could replace this alpha chromatic, alpha decorated proper coloring part as a sum of this this guy here. So some of the things in the left hand side. Okay. So we replace this guy with this guy. And there are quite complicated statistics on it. But our first claim is that this part given by word W sigma, this part is independent of the choice of tau. Okay. So in here, if you fix your bywords W and sigma, everything here are the same. So if the first claim is true, you can recollect all these as sum of K, sum of this guy. So sum of this guy with this particular thing, and then sum of tau due to the tau tilde. Okay. Oh, I'll just keep it tau. It's tau tilde, but yeah. And the second claim to make the argument simpler. And the second claim is that this guy here, sum of tau in alpha plus k choose n of q to the tau is given as q to the some statistics again, I minus 1 minus a cent. And then our desired alpha plus k choose n basis. Okay, so if you recollect everything correctly, then you will get the this uh ugly looking statistic and then this nice formula. Okay. So this is how we prove the monomial expansion. And of course, our question is, can we find um, alpha plus k choose n times Schur expansion of the alpha chromatic symmetric function? And yeah, this will be very interesting because, as I said before, this would give you a nice formula, even though it's not a combinatorial formula because you have to divide it by n factorial, but it would give you a very nice formula for the Schur expansion of unicellular LRT. And even if I'm not sure about this guy, but I, f- I feel like this is hard enough. So, uh, x alpha chromatic symmetric function at q equals to 1. And in here, unicellular LT polynomials are always as 1 to the n. So somehow you will get very nice properties when q equals to 1, but somehow finding the exact alpha plus k choose n basis, Schur expansion of this alpha chromatic symmetric function was hard enough. Yeah. But I think this is an interesting question. And that's all for me. Thank you for listening.
Thank you so much, Jason.
Thank you.
Any question for Jason?
Okay,
Yeah,
so
Brendan.
a kind of a broad thing. I think I've talked with both Jae and Jim about this, maybe not me, Sue. So in representation theoretic terms, what might we expect to see at the level of modules if you have positivity not in the Schur basis, but in like the Schur times alpha following
Yeah,
factorial or alpha plus k choose n basis?
that is that is very nice question that we don't know actually. So all these things are from like computation and combinatorics and symmetric functionology. And maybe root theory can be involved, but I'm not sure. Like in the root theory, the and in the very nice examples, you can find some Stirling number kind of thing in alpha plus k to n basis or alpha following factorial basis, and the coefficients are very nice combinatorial thing. But I haven't seen some nice like geometrical representation to that. Yeah,
Yeah, because you have this thing like if alpha is an integer, then with
yeah,
q
yeah,
you
yeah.
can think about a Kronecker product with a truncated polynomial ring. But yeah, cool.
Any other question for Jason? If not, let's thank him again.
Thank you.
Thank you so much. So that concludes our IPAC in July, and then we'll be back in August. I will send out a notification email later. All right, see you everyone. Enjoy FIPSAC.
Thank you.
You.
Bye.
Bye.